I'm sure you don't really care, but this is my second go-around on here. The first one, I realized some errors, and it didn't really make sense as I was talking through. So hopefully we can do a little bit better on the fundamental theorem of calculus. Eventually, tomorrow in the second version, or hopefully tomorrow, you'll be able to use the fundamental theorem of calculus to find a particular antiderivative of a given function. And by the way, we'll have to worry about what that word particular means. What I'm going to focus on here is showing you how to derive the other part of the fundamental theorem of calculus. And by the end of this, hopefully you can evaluate derivatives of integrals. So you're going to start with an integral, and you're going to take the derivative of that integral. And they're going to be a very particular type. One bound of integration is a constant. And you might think, well, aren't all bounds of integration constants? And you'll say, well, no, those can be functions as well. So part of the fundamental theorem of calculus you should already know by now, and that is if you're going to evaluate a definite integral, like this case, from 2 to 5 of x cubed plus 4 dx, you need an antiderivative. And so a good antiderivative for x cubed is x to the 4th over 4. A good antiderivative for is 4x. And we don't have to worry about that plus c. So we'll put in, do you remember, do we put in the 5 or the 2? So it's going to be the 5 first, so 5 to the 4th over 4 plus 4 times 5. And we're going to subtract from that 2 to the 4th over 4 plus 4 times 2. Okay, so that part we know. That's part of the fundamental theorem of calculus. We're going to worry about the other part. Something else you need to recognize is how to find the average value of a function. And if you don't already know this, I don't know. I have another video, or go back and look it up, but this is part of my proof. So how do you find the average value of g? Well, the average value of g of x is going to be the area under g of x on c to d divided by the width of that interval, d minus c. Or how else could we write this? And this is the form it's going to take. This is going to be 1 over d minus c out front times the definite integral from c to d of g of x dx. That's what we're looking for. Okay, so that's going to come up here in a minute. So we're going to start off with a continuous positive function. Since we're doing integrals, the continuous part should be pretty obvious. We don't want breaks on the curve. But something that's a little bit odd maybe is that I'm calling this f, not f of x. And we're going to come back to that in a moment. So we're going to choose some x value. And we're going to call it a. It doesn't really matter where a is. It just represents a starting spot. And then now we need to write some function, capital F, that gives the area below our f, right, this lowercase f. Okay, so let me think about it. So capital F gives the area below lowercase f. So I know that's got to be a definite integral of f. Let's see, it's going to be starting at a. All right, so starting at a, and the input is going to be x. Maybe we should color code that. So what that means is we're finding the area underneath lowercase f, starting at a and going to x. And then, well, f of what? And the answer is, well, not what I'm about to put here. I'm going to put something that's wrong, and that's f of x dx. Where'd you get the 3? I don't know. So that should be 8x. Okay, so f of x dx. Why is this the problem? I guess maybe we use 3. So capital F of 3 would be the area under this red f, starting at a and going to 3. So let's call this 3 for now. Of f of 3 dx. Well, the problem is f of 3, I don't really know what number that is, but f of 3 would be some y value. Okay, so y is equal to this horizontal line now. So now you would actually be finding the area not under this starting red f function, but underneath a horizontal line. So we can't do that. We can't have an x there. And we need to do something else instead. What we need to do is have what's called a dummy variable. So we can have anything we want there. We just can't have x. So let's just put a t here. Because, what's the difference between f of x and f of t? Nothing, I guess. We're just calling the input variable something else. But now let's see what happens when we use, let's see, the area underneath starting at a and going to 3. That would be f of, still f of t dt. We're now, cool. Now we are finding the right area. Still underneath that starting curve. So that's what we need. All right, cool. But let's change this back to x. Okay, I'm going to try to erase this. So now we want to find the derivative of this area function. Okay, well, that's not bad. And so that's pretty easy because that's, well, let's look at these pieces. So up here, f of x plus h, I guess this is a, this is x plus h, and f of x plus h, I guess, is all of this area. It's kind of hard to see, but that's okay. And then let's change colors here. F of x, what are we subtracting? That would be the area underneath red f in between a and x. And then, of course, divided by x plus h minus x. I guess we can call this f of t still. Okay. And so we're actually just going to rewrite that here. The limit as h goes to 0. Well, that's part of our derivative. Let's ignore that for a bit. Oh, where'd green go? So instead of f, now we have the definite integral from a to x of f of t dt. That's this part here, like we said. And then what's this first part? The definite integral from a to x plus h of f of t dt. That's what we had originally up top. That's, well, the area under this curve, that's that original f function we had. Okay, the denominator simplified to be just h. And so what changed here? Well, the thing I pick out is this, minus sign turn to a plus sign, but you'll also notice, not just that, but these bounds of integration changed. Instead of minus the definite integral from a to x, we have plus the definite integral from x to a. If you don't see why that helps or what changes, let's rearrange. So now we'll write that second integral first, and we have the definite integral from x to a of f of t dt plus the definite integral from a to x plus h of f of t dt. And we know properties of integrals. That's just the same thing as the definite integral from x to x plus h, keeping everything else the same. So what I want you to see here is this top part. Well, what is that? The definite integral from x to x plus h, that's this area. Underneath f of t, between x and x plus h, but we're dividing by the width. We're dividing by h. And so what do we get? Maybe you want it in this form. We have the area divided by the width. This is the average value of, maybe I'll make it red, f of t on x to x plus h. So, I don't know, as I've drawn it, that seems like a good average value, somewhere right, maybe right in the middle. I don't really know, but, we're applying a limit. And what happens when we apply the limit? Well, let's go back to this one. This is a little bit better. H, that definitely doesn't look like 0. So, this side's going to slide in. And when we shrink h to 0, maybe x plus h now moves to here. And then x is here. So we would still be finding the average value. Ooh, that's too high. And maybe the average value is something like that. Except, I wouldn't really say h is going to 0 yet. That's not really close. We've done enough limits. By the time we're done, x and x plus h are going to be on top of each other, basically. And so what will we really be doing? We'll be finding the average value of, let's do it again in red f of t dt from x to x plus h. Except for x plus h and x are in the same spot. So it's kind of like it's at x. So what did we do? Well, we applied a derivative to a definite integral. And what did we get? Well, we got the function we started with, right? What we got was f of x. We got the thing inside. And so the big idea is, hey, integrals and derivatives are inverse operations. Let's hammer that home with a couple of specific examples. So here's what we had to do. We're going to take a derivative of a definite integral with one bound of integration that's a constant. The other bound, and for now it's going to be the upper bound, is going to be the variable x. So it says find dy dx. So I know this t and dt, those are dummy variables. And so really the variable, the input, the thing that could change is, hey, we're finding the area underneath cosine, what the heck is pi, starting at pi and going to some x value. Cosine of t, that's our function. And so, we're finding, this area going up to whatever x value we choose. And so, well, if I'm going to find the derivative, first let's get rid of all the unpleasantness and just rewrite this as y is equal to antiderivative of cosine of t is sine of t. Is that right? The derivative of sine is positive cosine, yeah? Evaluated from t equals pi to t is equal to x. And so, let's see, y is equal to sine of x minus sine of pi. Okay, that looks way easier to take the derivative of. And in fact, it is really easy to take the derivative of. So dy dx, derivative of sine of x is cosine of x, and the derivative, well, it actually doesn't matter what sine of pi is. Sine of pi happens to be 0, but what we know is sine of pi is a constant, and the derivative of any constant is going to be 0. Okay, so the derivative of a definite integral from pi to x of cosine of t dt ends up, with cosine, the thing inside what we started with. So what do we think we're going to get here? Y is equal to the definite integral from 0 to x of cosine of t dt. Let's try that again. Well, so y, and we're starting somewhere else. Maybe there's cosine. This pen isn't working great for me. Cosine of t, that's our function, and we're starting at 0 and going to x. Okay, so let's see. Y is equal to antiderivative for cosine is sine of t from t equals 0 to t equals x. And so y is sine of x minus sine of 0. And pretty easy to take derivatives again. The derivative of sine of x is cosine of x. Not shocking. We pretty much get what we start with. Plus 0. Oh, that's the wrong one, but we get the exact same thing, which is a little bit weird. So the definite integral from 0 to x of cosine of t dt, the definite integral from pi to x of cosine of t dt, both have the same derivative. Let's see if that holds here for, well, so we want cosine starting at pi halves and going to some x value. All right, here we go. So first we'll evaluate the definite integral. So sine of t from pi halves to x. And then y is equal to sine of x minus sine of pi halves. And then again, it doesn't matter. That's super weird. That lower bound of integration doesn't matter. The derivative of the derivative of sine of x is cosine of x, and the derivative of any constant is going to be 0. So can you explain what's going on here? I showed you pretty specifically, hey, those last 3 examples, the lower bound of integration didn't matter much. Pi halves, but 0, or pi, as long as the upper bound is x and the integrand is the same cosine of t dt, we got the same derivative. Well, let's do a couple more examples with different functions. You'll have to answer that on your problem set. So for now, we're going to evaluate these definite integrals and then take the derivative. In the future, we'll skip over part of that. All right, so let's see. Y is equal to, what is an antiderivative for 2t? That'd be t squared. And that's going to be from t is equal to 7 up to t is equal to x. So y is equal to x squared minus 7 squared. I'm not going to write 49, and you'll see why here in a second. What do we get? dy dx. That was our goal. Find the derivative of y with respect to x is 2x plus 0. The derivative of 7 squared, the derivative of 49, the derivative of any constant is 0. Well, this one might be a little bit more difficult. We just need to use substitution. So let's see. Y is equal to, you know what, let's skip this one. That's a little too hard for not being in the same room. Hopefully that's enough for you. I'll upload my solutions to your homework so that way we can all agree.